Okay, so welcome to the presentation, and this is Derek. He did his semester thesis with me and Elia. Oh no, sorry. With me and Anko, and also and yeah, the stage is yours.
Thank you. So yeah, welcome everybody to my presentation on collaborative aerial transport using deep reinforcement learning. So I want to start with a little video. So this was a video I recorded in like 3 weeks into my project. I had the privilege of going to one of these test days in the flying arena where I saw the policy from Yunlong, the deep reinforcement learning agent, in action against Marvin. And it was really an inspirational moment for me that really put a seed into my mind for the vision of my project. And this vision was really to take this agility that you see here in this drone, driven by reinforcement learning, and put it into a system where this drone would not only be flying by itself, but it would be collaborating with other drones and carrying a payload. So you might think that this vision is cool, but what are some other advantages of a team of aerial robots? Well, a team of aerial robots can provide more controllability and maneuverability, so you're able to control the 6 degrees of freedom of a payload with more flexibility and have more configurations. It's also more robust to failure of one of the quad rotors, and it's more efficient. So if, for instance, you're a delivery company or something, you don't have to size every flying platform for different types of payload, but you can have a single flying platform and just change the configuration to carry different types of payload with different masses. So yeah, these properties are really useful in applications, as I mentioned, such as delivery, but also search and rescue or construction. But it also comes with some challenges. So collaboration of any kind, such as what you see here in the DARPA challenge, for instance, is very challenging. It requires sensor fusion, not only across the sensors within one vehicle, but of sensors across vehicles. It requires communication between either the different agents and a central unit, or between the agents themselves, and coordination as well. So planning for different agents. And if that interaction is physical, then there's additional challenges, because now the dynamics are coupled between the agents, and the fact that they're in close proximity means that there's likely interference between them. So this could be aerodynamic interference or of other kinds. And now the fact that these agents are in proximity, it also means that you really have to do multi-agent control by keeping into account or being aware of the other agent's presence to, for instance, avoid crashes, and keeping in mind that the actions of one agent directly change the environment of the other agent. So let's look at some related work in the field of collaborative aerial transport. So there's been many approaches in the last years trying to tackle this problem. So one of them is, for instance, geometric control, MPC, and both of these methods that I showed were tested in simulation. But at ETH there's also been some work on a physical platform using passive force control, where there's a force sensor on the slave, and it's able to basically follow the plan of the master. And there's been some work also in Professor Loiano's group and here at RPG, where instead of using a force sensor, there's a vision sensor. So the last approach that I wanted to touch on is quite an early approach, which is Skynet at the flying machine arena. And this was done with optimal control, and is, out of all the approaches, the one that showed the most agility. So with all the approaches that I've shown, there's some limitations. So either these approaches are not agile, so the top speeds that are reported are in the range of 1 to 2 meters per second. Sometimes they're not tested on physical platforms, so a lot of the results that have been reported in this field are just in simulation. And in the case of Skynet, which is agile, it's been tuned for a very specific task. It's basically a discrete set of time steps, time ranges, where there's been an optimal trajectory plan that has to be tracked online. So what we wanted to do was address some of these limitations by looking at reinforcement learning as a potential method. So reinforcement learning has been applied quite extensively now to flying robots, but I just wanted to highlight some of the work that has been done that kind of goes in the direction of where we're headed, which is collaborative aerial transport. So Alexandra Faust did some work in her PhD on learning swing-free trajectories, which was with Q-learning. There's been some work recently at Levine's lab where they use meta reinforcement learning. They learn to learn a changing dynamic model mid-flight. So in these pictures you can see that as the agent is taking off, the load is basically increasing and it needs to know how to handle that. And of course there's the work in autonomous drone racing in this lab by Yunlong that has really demonstrated the ability of reinforcement learning to be able to learn agile flight. So we basically wanted to take this and apply it to collaborative aerial transportation. So our goal would be to be the first to apply deep reinforcement learning to collaborative aerial transportation. So how would we do this? What was our approach? The first step would be to implement a dynamic model from scratch in MATLAB to be able to quickly debug and test it and validate it. Then once that was done, we would port this model to a FlightMare environment in C++, and there we would use the existing framework, this OpenAI GYM-style framework, to train a centralized reinforcement learning policy using PPO. So let's look at the first step in this process, which is to implement the dynamic model. So for this we used a state-of-the-art model that was presented in recent work at Professor Loiano's lab. We implemented this model from scratch, and some of the properties that I want to highlight of this model are that it's a slung load model, as you can see from the picture. The links are rigid, so they basically keep their length and they can be compressed and in tension. And this also means that there's a kinematic relationship between the payload and the quadrotors. And it supports arbitrary points of attachment on the payload, so not only a point mass, but any kind of payload shape. And lastly, it also supports an arbitrary number of quadrotors. It doesn't get harder to implement or something, it's just a parameter that can be changed. Which increases the dimensionality of the state, but it's easy to support that. On the deep reinforcement learning side, once we had the dynamic model implemented, we had to make it into a FlightMare environment, and then we would use proximal policy optimization to train a centralized policy. So as you can see in this diagram, you get an observation from the environment, which is normalized. Then we pass this through a very similar architecture as what was used for drone racing for a single agent, and the output is basically a stack of actions for each quadrotor. So the size is 4 times the number of quadrotors, and it's a thrust rate. So you control the body rates and the collective thrust. So how are we going to learn to hover, which is going to be the first warm-up task to see if this actually works. For this, we selected the following observations. So you see that the core module is the same as what I showed in the previous slide. We're just changing the observations. So we're feeding it the payload position, the quadrotor position, and orientation, and linear velocity. So this is for each quadrotor. You see that the observation space becomes larger as you add more quadrotors. And then we also have the rewards that we're giving as feedback. And for the reward, we have a goal state, which could be bringing the system at rest, but at a given position for the payload. So the payload should go to coordinate 0, 0, and height of 5. And then we take the difference between the current state and the goal state. We take the norm of that for each of these individual features, so position, velocity, orientation, body rate, and linear velocity. And then we use a negative exponential as the reward. And then this, as I said, stays the same. So what do the results look like? This is for one quad rotor. I've shown here at the bottom the dynamical properties that we're using. As you can see, it starts, this is the trajectory of the payload, by the way, and the velocity of the payload. We start at a random point on the map, and then we fly to our desired position, which is a height of 5 and in the center of the map. And you can see here on the position plots that it's indeed tracking, it's going to that position and then being at rest. You might ask why there's so much noise in these plots. Well, we have a body rate penalty, so we want the body rate of the quad rotors to be 0, but in this experiment it's not really visible here, but the reward for the body rate is actually all the way here at the bottom. It's this horizontal line, so the coefficient for it is too low, and given the dynamic model, which is you have a spherical joint on the quad rotor can basically be doing this, and it will not impact the rest of the states of the system. So it's basically not being penalized for this. Yeah, so this is what it looks in visualization. It's gonna loop another time, but yeah, it starts at a position and then it flies to a waypoint and hovers there. Now we extend this, we make this a bit harder. We extend the observation space to 3 plus 15 times 3, so 48, because we have 3 quad rotors, and the action space is 4 times 3, so 12. And we see that it can still manage to perform the task. So we see that it's the payload is this red line, and it's going close to the desired goal state, and it's at rest. And this video will also show you what's happening. There's something interesting here, which is that, at least when I saw this for the first time, the configuration isn't what you would expect it to be. But this again can be brought back to the rewards that you're giving to the agent. There's no reward that is linked to the thrust on the quad rotor. So in this case, it's basically learning that one of the quad rotors is taking most of the mass of the payload, and the other ones are basically just hovering next to it. And yeah, it's a valid solution. Okay, so now we got very promising results in this hover task. So we thought, how can we really push the system here to the next level and give it an even more complex task? So we thought, what if we tried to race with the payload through the gates and letting the quad rotors figure out how to control the payload? So yeah, so here recall this was the architecture for the hover task, and one of the nice things about this method, which I really like, is that we can basically keep the core module the same. We just have to change the observations and the rewards to be able to go from this hover task to a much more complex racing task. So in this case, when we want to do racing, the observations we're giving are the relative distance between the payload position and each of the gate corners of the coming gate, or the next gate, the linear velocity of the payload, and for each quad rotor, the orientation, the linear velocity, and the direction of each link. And then the reward is basically the gate progress reward. It's actually a more simple reward than the one in the hover case. It's just the difference between the previous gate distance and the current gate distance. And given this, with one quad rotor, we get promising results. So what you see here is the trajectory of the payload, and it's managing to go through all the gates and at quite high speed. So the lap time here is 6.8 seconds, and you can see that the thrust profile also shows that the quad rotor is pushing the platform to its limit. And this movie shows kind of what it's learning to do. Yeah. Okay. So let's take it a step further and try to race with 3 quads attached to the payload. We see very similar results. So an even faster lap time this time, 5.84 seconds. And again, a thrust profile that shows that the platform is being pushed to its limits even with 3 quad rotors attached to it. The observation space here is 60 dimensions. And this is what it looks like. So again, the links of the model are rigid, which is what gives it a slightly unrealistic look, because the payload can be pushed from behind, essentially. And there's also no limits on if the quad rotors go against the links or anything. So they're really free to collide with anything. The only collisions that are counted are the payload with the gates or with the ground or the walls. So, yes, let's look at what we've achieved, first of all. We've taken a step towards agile collaborative flight, and we've shown that deep reinforcement learning has potential in this field. And aside from that, we've built a flight mirror environment for training collaborative agents carrying a payload, which can be used to do a vast number of other tasks. And of course, this being the first step in this direction, we have a lot of limitations. First of all, we have a centralized policy. So this means that you need some form of communication of either all the drones with a central unit that's going to gather all the states or the states necessary for the observations and then send the actions to the drones, or you need the drones to communicate with each other, their internal states, so that they can all run this policy on board. The dynamic model that we initially implemented was from another paper, and most of these papers have not tested anything at high speeds or in aggressive flight. So this model actually is not really suited for high speeds. It doesn't have aerodynamics, and the quad rotor model that it's using is also it is not really a quad rotor model. It's just a rigid body with thrust. And the policy. So the policy also is not robust against dynamic property changes or different tracks, because we haven't trained with randomized tracks or randomized properties like the mass of the payload or the lengths of the links. We have randomized the initial conditions, so the states, but not dynamic properties. And lastly, the observations that we're giving the agent are noiseless. And in some cases, well, as I showed you, they have quite high dimensions. So we're giving the policy quite a lot of information. For instance, the link direction, which is something that in the real world would be kind of hard to estimate. It would require a motion capture system. So the outlook for this project, the next steps would definitely be to transfer this policy to the real world, and to do that, we'd have to address most of these limitations. So we'd have to adapt the dynamic model to have a higher fidelity quadrotor model that can deal with actuation delay, that has the low-level controller integrated. We'd also have to add aerodynamics to the payload, and we'd have to randomize property changes and track changes as well during training. With that, I would like to thank you all for being here and for listening to my presentation.
Can you show again the objective function?
Yeah. So for racing or for?
For racing.
Wait. This.
So what are you trying to optimize?
We're trying to maximize the gate progress, and then there's also
The gate progress of what? Of the center of mass of the.
Yes, of the center of mass of the payload. Yeah. Exactly. And also there's also some sparse rewards that I haven't added here, or sparse penalties, which are linked to collisions. So you also don't want to collide with the gates or the ground.
Nothing. None of the quadrotors, none of the payload.
No,
so
only the payload.
Can you elaborate exactly?
Yes, so only the payload.
So the quadroons are allowed to actually collide and pass through
Yes.
through all the gates.
So that's
And
another.
the wires.
Yeah.
I see, I see.
That's another thing
I
that
see,
would have
okay.
to be
So the
addressed.
gates are basically kind of virtual.
Yes,
I see, I
yes.
see. Okay.
Yeah. One.
And then gate passing error as well?
You mean that safety reward?
Yeah.
No, that's also not added here.
No, but you want to pass to the center of the gate, right? As much
No,
as possible, no?
no, that's not. So that's part
Just
of
maximize the progress. That's all.
maximize
you
the
want.
progress. That's it. Of course, that's probably one of the next steps you would do to be more robust, and that's what.
So what are then the rewards? So if it's only one reward?
It's really just this. I also added a body rate at the start of training at some point, but to minimize any crazy behavior on the quad rotors, but I didn't see that it made a huge difference. And actually, here you can see that the body rate is here, but it's like at 0. I didn't really care about it. The quad rotor angular velocity reward. So you can see that the
So
total reward.
at the beginning you added this, but then you removed it.
I tried it with, and I saw that it didn't make a difference.
Can you go back?
Yeah.
But then what are the other 3 rewards?
3 rewards for hovering or for.
Position, velocity, what is it? Position.
Yeah. So this is basically this part is the current gate distance, so the difference between the payload position and the gate center position.
So there is, I asked you about it, you said no.
Okay, yeah, so it does have to go through the center of the gate, it's the progress towards the center of the gate, so sorry, yes, then it does want to go through the center.
Can you be more specific? So what is the reward at all? What happens if you are not close to the center? How close do you need to be to the center to be considered a positive reward?
Okay, so like there's no so the safety reward, I think you're referring to the one that was in the paper by Yulong for autonomous racing. We showed you like a gradient map where the closest you were to the center, it will give you an explicit reward. But here there's no. It's really just this. So the closer you are to the center of the gate with respect to the last time step, the higher the reward. And then once you pass the gate, it's all with respect to the next gate.
So there is a reward, a gate passing reward.
Yeah.
I mean, you listed that, right?
Yeah.
Good. Thanks.
Yeah? Go ahead.
Sorry, so you don't model any downwash, right?
No.
Okay. But with the case, with the single attachment point, with the single drone,
Mm-hmm.
do you think it would work in reality?
You mean this?
Yes.
I mean, there's many inaccuracies in the dynamic model, and aerodynamics is one of them. But I don't think that when implementing this on the real world, that downwash would be the biggest problem, because we'd probably have a system where the payload is relatively small. So yeah, it wouldn't be like this big of a box with this big of a surface area. So then the downwash would probably not have that big of an impact.
But you model the rotations of the box, right?
Yeah.
Have you tried to add some noise to that, or?
So we've added noises, and we've randomized the initial states when we reset the environment, but we have not added noise to the observations.
Okay.
So, yeah. This was really the first step, and we wanted to know if it would work in the best of scenarios. And now the next step would be to make it harder by doing these kind of things.
Okay. And then there are like spherical joints both on the quad size and...
Yes, exactly. Spherical joint here and spherical joint here on the center of mass.
Okay.
Yeah. Yeah.
Okay, thank you.
Yeah.
Thinking about the real world application, probably in the long run what you want is something that is not centralized and that does not require this very accurate information about your payload. So for now, not thinking about the not centralized thing. How do you think would you need to extend your approach that you can fly around with boxes that you don't know how heavy they are exactly? Of course you can lift them, but you don't exactly know this thing is half a kilo. What do you think?
So what kind of range are you talking about? Like, which you did?
Okay, so
Does
for your case, the boxes are going to be between 0.1 and 0.5 kilometer, but you don't
Okay.
know.
But can you train using that knowledge of the range of masses it should be able to handle? Because
Yes, you can.
okay, because yeah, then you would try to do that to during training randomize the payload in the range of allowed masses, and then it would figure out a way of dealing with that, I assume. But to your other question, which is the decentralizing the policy, yeah, that's probably one of the biggest challenges, because you would need to the observations would have to be only onboard observations, so states that can be inferred on board. And you would have to use an approach similar to what was done here at the lab, or by Professor Loyano's group, where you use sensors on board, like vision sensors or force sensors, to estimate things like the tension on the cable or the direction of the cable, and the position of the quadrotor with respect to the payload. If you put, like, for instance, an April tag on the payload and you have a downward facing camera or something, you could get something. Yeah, your goal is essentially to get something close to this observation, but from only onboard sensors. But again, there's many things that I haven't tried here. So the next step would also be to try to see how small I can make this observation vector, so that I can still race.
Exactly, yeah, but my question, it seems you dodged the question a bit. My question wasn't about centralized or not centralized. So you mentioned you could randomize the payload at training time and the policy would figure it out. So, what do you think how would the policy behave if you start randomizing the payload without changing anything about the observation? Do you think this would work out of the box, or do you think?
Yeah, I think it would. I think it would work, but you would have lower performance on average. So it's similar to what Yulong had when he tried to randomize the gates, where basically he wanted to be able to race on any random track, and there he observed this behavior where the average lap time would decrease quite a lot, but it would still be able to handle a higher number of racetracks and not crash.
Yes,
But I have not tried this on a dynamical property.
I think an important thing would be that the policy can somehow figure out how heavy that box is, and I think the key to unlock this would be to have a stack of observations.
Do you mean like the observations to have some memory or some like?
Yes, exactly.
Okay.
Yes.
Yeah.
Thanks.
Yeah. Okay. I see no more questions.
Okay.
Cool.
So, yeah.
All right.
No more questions. So thank you.
Thank you.